Hi, I'm Ted Hahn.
I'm Mark Hahn.
I'm an SRE for hire working on planet scale distributed systems. My clients include big corporate enterprises like Epic Games and smaller startups in Seattle, New York, and worldwide.
I'm director of cloud computing and DevOps for Ciber Global consulting firm that's nationwide. And in this role, I'm kind of responsible for everything related to software velocity for our hundreds of consulting teams that work for our clients throughout the country.
We're a father-son team. We're in the same space, and we like getting talks together. Yeah.
So the motivation for this talk is you want to run a secure application. How do you do that? Well, number one, you run TLS and you encrypt everything in transit.
We're talking about encryption in transit. We're not talking about end-to-end encryption. We're talking about applications and APIs that need to secure their communications between every pair of communicating components. Again, encryption in transit. End-to-end encryption is when two clients communicate with each other securely, moderated by a third party sometimes. So if a message is encrypted on your phone, sent to a server that can't read it because of the encryption, and then sent to another phone that then decrypts it, that's end-to-end encryption. We're just talking about encryption in transit, that your communication with the server is encrypted. The server can read whatever it is and then send it on to other applications or other clients.
Right. Encryption in transit is much more malleable. So let's talk about the basic building blocks for this. So we'll talk about the public trust domain.
So what does a certificate actually say? We sometimes summarize it as this website is trustworthy, but that's not really a judgment call that the computer can make. It's also referred to as the website is who they say they are, but it doesn't really say that either. What certificates can prove from a mathematical standpoint is that some authority, some other private key that you trust, asserts that this certificate has is this website, and that you are communicating with the holder of the private key associated with the public key in the certificate.
Right. So browser vendors and operating systems maintain a list of these public CAs, these public certificate authorities. They're not 100% the same across all of these things, but in most cases, the differences don't really matter. They practically mean the same thing. So if you go to the appendix of our presentation, when you look at the repo, you'll find links to the management advice that these vendors provide for dealing with TLS. So you've seen this before. This is what a certificate looks like when you open it up with OpenSSL X509. And these are the components of that certificate. There's nothing that's really strange here. Let's talk about them in a little bit more detail. How are these certificates composed? Well, they're the primary things in here are the things that you would expect, right? There is a public key that you can use for encrypting and talking to this server. There's also the signature, that the certificate signature that comes from this certificate authority provider. There's a serial number that's used by the CA for internal tracking. None of this really matters that much, other than the public key. What really matters in terms of how TLS is working these days are the certificate extensions that have been developed over the years since the RFCs were originally released.
So yeah, most of the magic of a modern X509 certificate is in extensions. The most common one you'll see is subject alternative name, which contains DNS names or other names. It can be email addresses, it can be URIs, it can be IP addresses, but generally on the web, certificate authorities will only sign DNS names.
For SMTP, it might be different.
Well, also SMTP. There are separately X509 certificates for SMTP servers, and that is a usage.
Whole different talk.
So there's extended key usages, which is an older extension, and extended key usages, which is a newer extension that says things like this is used for web server authentication. or web client authentication. If you go to most CAs, they will sign you for both. They will also use digital signature and key encipherment because those are usages that you use to initiate a TLS connection. There's basic constraints, which says whether or not it's a CA. And then the subject key identifier and authority key identifier, which are derived from the public key and identify uniquely a public key that can be used to build the chain of trust.
Again, so the subject key identifier is the identifier for this certificate, and then the authority key identifier identifies the next level authority. It identifies the certificate that has signed this certificate. So, and if you follow that chain, you can get up to root certificates, which is that those public CA lists that we've seen before. It's also worth mentioning that you can get information about these certificates through the authority information access information, including ways to validate if the certificate is still has been revoked or not. And then there are the certification policies, which are the formal specifications of the human understanding of the rules around using this certificate.
What trust has been associated with them.
What trust the CA has vouched for in this certificate, right?
Okay. So
this is the TLS protocol. So we've got the certificates. The certificates form the basic building block of the TLS protocol. So at the beginning of a TLS session, the client will say hello to the server and tell the server what domain, what website, web server it thinks it's talking to. That is the server name indication, SNI on this chart. And then the server can use that to pick the right certificate that it returns. Then the client says, hey, here are the cipher suites I know about. Let's pick one of those. And the server picks one and sends it back. And then the actual HTTP discussion can take place. In TLS 1.3, they've optimized this. They've removed one complete round trip, which makes the system simpler and faster. And in security, simplicity is our friend. So we want to go for simplicity wherever we can.
Another big improvement in TLS 1.3 is a simplified set of cipher suites. There are 5 of them. They are simple. They are predicted to remain secure for the next 10 years. If you are using TLS 1.2, there were 36 cipher suites, including some that were debugging and not reasonable for use in actual communications that you could turn on and off. In TLS 1.3, there are 5. You just use all 5 of them. Any of them works. Any of them work.
All of them are strong.
Yeah.
And as Ted said, they're the expected lifetime is greater than 10 years. Hence, kind of the time frame at the beginning of our talk that this talk is advice for the next decade or so. So we'll do this talk again in 10 years.
Yeah. There's a great write-up that we've linked here about TLS cipher suites that the Go developer blog just put out. So go read that.
So part 2, let's talk about how these building blocks are used to develop trust on the web. So
you've got a certificate. What should you do with it? Well, first off, you should use a certificate provider that uses certificate transparency, because that way you have a record of all of the certificates that certificate authority has issued, and you know which ones are still out there and still valid, and you know which ones should be revoked and have been revoked. You should use short-lived certificates. 90 days is the standard with ACME, and you should use short-lived certificates because the shorter the certificate lifetime, the more trust that you have that it hasn't changed, that there hasn't been some change to whether or not you should trust it, that the information is still valid. HSTS is a header that you can add to your web services. Strict transport security, HTTP strict transport security is what it stands for. And it tells your browser that you should only connect to this website over HTTPS. Once a browser has seen that, it will no longer attempt to connect over HTTP, and that's good for your security. And you should set up cookie management properly. So all of your cookies should be set with the secure attribute so that they're only sent over your HTTPS site. You'll want to set the domain attribute, and you'll want to set the same site attribute, so that your certificates are not sent with third-party requests. That helps prevent XSRF, cross-site request forgery.
Right.
And helps prevent you from leaking cookies from multiple different parts of your site.
Right.
And use separate domains to separate different parts of your website.
Right. So how do you get certificates into applications? For the most part, the easiest way to do this for your public facing stuff is to use the certificate capabilities of your cloud provider. So use the cloud provider to load certificates into your load balancer. And the cloud providers make this very easy to get the certificates and manage them in your load balancer, and it offloads a lot of this difficulty for you. The other way to do that is use a certificate provider that uses the ACME protocol. This way, you can automate the generation of certificates and the update and the rotation of certificates throughout your infrastructure. ACME is a great tool for that. So, and there are a number of different, like if you go to the ACME, if you look up ACME. There are a lot of different ways to get ACME certificates depending on your particular technology stack and the infrastructure that you're using. So either of those two ways work well.
So this is a purely practical slide. It lists how to configure your load balancer. These are security policies for the major cloud load balancers. Use one of these. Use the one associated with your load balancer, or use the Mozilla configurator to set up your configuration. It has information on different common proxies and different common programming languages for how to configure your TLS implementation.
Yeah, the Mozilla configurator is great.
Yeah.
So this isn't strictly TLS advice, but it is application architecture approach that helps you simplify your life in using TLS. So what we recommend is, we said before, use separate domains. Again, you've got an external facing website that contains your marketing stuff. It probably contains your application. The endpoints that your application uses, or your phone app uses to talk to your system. So use those. Use one domain for that. Then all of your corporate applications, all of the stuff that your business users use that your customers don't, use a separate domain for that. Call it corp and segregate this off. And that way, when business users log into the business level apps, their cookies don't commingle with the cookies that you're using for your public facing stuff. So you can be both a customer of your web app and a corporate user, and those cookies don't cross, and there's no trouble with that. So this is that example is just a starting spot for URL organizations.
But this one is even better. Go all the way to using multiple subdomains and setting them up with common subdomain trees. So if you have your front end website probably has a marketing site, and you don't want your marketing site, you want that to be a perfect, purely static site. Set that up on www and serve your interactive application from app.example.com, and put all of the components of that at their own subdomains that can have their own cookie subdomains, or that can share by having a common root, while not also leaking that to your static website, which is probably hosted at, Squarespace or Wix or just an S3 bucket. Separate those out. And your corporate apps should be the same. Separate out each of your corporate apps, give it its own subdomain, and make them available on the public web using public web certificates.
Exactly. So now you're using certificates. The next thing is, even though they've got, specified lifetimes, sometimes things can go wrong. So you need to do revocation of trust.
Yeah. Certificate transparency is not part of is not a revocation method, but does guarantee, it does show you what you need to revoke. Certificate transparency, if your CA supports it. If your CA is using certificate transparency, there's a list of all of the certificates they've issued. That allows you, and you can go scour that list for if someone else has issued a certificate in your domain name. You can go figure that out. You can go get that shut down and get that revoked.
And update all of your infrastructure at the same time because something's gone horribly wrong. But that transparency is what you need. So in the past, there have been multiple ways of doing certificate revocation lists. The browsers still support them, but they're pretty slow moving and they're not a panacea for all this stuff anyways. Then there's the protocol OCSP, the online status protocol, which turned out not to work very well in practice. So ends up being basically dead at this point.
Yeah.
OCSP is not something you should worry about. Most modern browsers don't support it at this point.
Well, do support it, but don't trust it. Don't trust. Don't consider it a failure.
Yeah.
Don't use it. Don't check it. There. So we've talked about trust on the web. That is one trust domain. We're introducing this concept of a trust domain, which is an abstract concept, right? The web is one trust domain, and you trust certain things about websites. You trust certain things about the set of sites that are trusted by CAs. But there can be multiple trust domains. So we are talking about certificates now as the building blocks of a trust domain. You create a CA or multiple CAs, some intermediates that do the actual online signing, and some claims they are making, which X509 is used to represent. And that the web as a whole is one trust domain that works with that has CAs, intermediates, and claims that you can trust based on that.
So let's talk about a local trust domains. We've talked about public trust domains. Let's talk about what it takes to do a local trust domain, which basically relies on using a private certificate authority, one that you run, not one that's generally available to the web. So first of all, you're going to split your zones of trust. And so by this means, we mean your trust domains. So you have a zone of trust for all your public facing stuff. And that should use public certificates from a public CA that chain to one of these public root keys that we've talked about. That goes in your load balancer, and everything that's outside on the other side of your load balancer, all that public stuff talks through uses those certificates as their root of trust. Then internally, you run another CA, and this inside that CA, you push those certificates to your internal infrastructure, your internal applications, and so forth, and then they can trust each other. But should they, go to the web, nothing from the web can actually talk to them unless they have they know the internal CA.
Nothing from the web will trust them because they don't trust the internal CA. But your internal applications can trust each other. Okay. Here's a realization of that diagram where your Kubernetes cluster automatically issues certificates to every pod, to every deployment, and so they can communicate with each other across your local trust domain. You run your own CA, and everything within your cluster knows when it's talking to everything else within the cluster that it is talking to the right stuff. This secures your Kubernetes cluster. This secures your infrastructure against man-in-the-middle attacks that have the ability to sniff and inject traffic. And so long as the control plane, the Kubernetes control plane is secure, which it is because it uses actually a CA and precisely this in practice.
Yep.
So long as the Kubernetes control plane is secure, man-in-the-middle attacks are not possible between your web servers.
Right. So we'll talk about methods for using building and running a CA and how you use that throughout your infrastructure. We'll talk about these are all very fine methods for building an internal CA and using that to distribute certificates. But before you jump into actually building out one of these things, it's important that you actually have a trust model for this internal trust domain, and you understand what that trust model looks like. It's actually pretty simple. Ted, explain it.
Yeah. So The trust model for your internal trust domain is pretty simple. You just have a CA bundle that represents your CA. You have maybe an intermediate, and then everything trusts everything because they are all connected with the same CA bundle. You create a CA bundle and you create a certificate and key for each of your internal servers. You create an HTTP client on each of your internal applications. And when they go to communicate with other internal applications, they expect those internal services to be signed by, to have certificates signed by your internal CA. It's all just one trust domain, just using SNI to make the claims. And that's good enough. You use short certificate lifetimes. You don't trust this for your public roots of trust. So if you have an HTTP client, if you need to go talk to the web, go talk to the web with a different HTTP client in your application and have a second instantiation of your HTTP client that trusts your local applications. Don't overcomplicate it. Revocation and certificate transparency are great to have, but you are so much safer just having trust between your things that's not a requirement to make this work.
Right. And remember, you have your hands on everything in your internal domain. So trying to do distributed revocation is not necessary, just getting started out. Yeah. So doing this is really a leg up. Yeah. So if you go to our repository, we've got advice on running each one of these different domains. So Cert Manager is a piece of software that runs inside a Kubernetes cluster. It's built for Kubernetes. Are you okay?
Yeah, just cricking my neck.
Okay. So Cert Manager runs in Kubernetes and it can run as an internal CA, and it also can run as a front end to ACME certificates. So we can go talk to an ACME provider and deliver certificates into your infrastructure. You can run the Let's Encrypt CA. So that software is called Boulder. You can run that in your infrastructure, and it supports everything that Let's Encrypt does. And that gives you everything you need to build and distribute certificates.
Yeah, Boulder handles certificate transparency and OCSP requests for you. Vault is another popular choice. It's a secrets manager first and foremost, and TLS keys and TLS certificates are secrets. It can be used as a backend to certificate manager to sign certificates. And what you can do with it is you can put your CA or your intermediate CA into your Vault instance, and then using role-based authentication and rules configured in Vault, you can pull out signed certificates, dynamically generate signed certificates or private key and certificate pairs signed by that CA.
Cloudflare CFSSL is a great way to build. You can write scripts around CFSSL and build a really robust infrastructure for generating certificates. It keeps a certificate transparency log that you can use. Yeah. So this is a great way to automate. It's useful in lots of different contexts because it's just script based as you go forward.
It implements a signing server, so you can build a signing server sort of like ACME with it. And it will keep an OSCP log or OSCP server up. It will keep a certificate transparency log. But it is sort of build your own, like it is an incomplete implementation that you go and modify. You modify the source code and rebuild to make your own version of it.
Okay. You can use Istio. Istio includes a CA inside it, and so it simplifies deployment. If you've got Istio infrastructure and you've bought into that, then using the CA issuer, the CA in there is a great way to go. It knows where all of your applications are and can deploy certificates to there. It also provides proxies for your traffic, which is a model that works well for many organizations.
Yeah. And then there's cloud HSMs where they will run a CA for you. And you can use the cloud providers RBAC tools to control who can issue certificates from that CA. Yeah. The advantage of an HSM is that it runs on dedicated hardware.
Can we define the term HSM?
Hardware security manager or hardware security module.
Module, I think.
Yeah, module. The dedicated hardware has a lower attack surface, but the downside is it's expensive. It's expensive to run. It's expensive to use. There's a limited number of certificates per second that you can issue from them, which is both a boon and a curse to your security, because if you're rotating very fast, then there may be some limit to how fast you can rotate and how many clients you can support at that point.
But if you need that level of trust, it's available for you, and definitely take advantage of it.
Yeah. So here is a reprise, a summary.
How to get certificates into your application. So first step is, as you issue certificates, put that private key, that certificate, and a CA bundle into a single clear folder that's secured for for the application to access. So this is relatively easy to do with modern tools. In Kubernetes, you can bundle that into a secret. Istio and Vault will help you do that. They'll bundle them into their own secrets that your application can access. That is a great way to do that. Generate certificates that include both the use as server and use as client tags in them. That way you can use them on either side and ensure mutual TLS. So as your internal infrastructure is talking to other parts of your internal infrastructure, they can take their server certificate and present it as a client certificate. And this is a leg up in terms of security. Anyways.
Yeah, requiring authentication, you don't necessarily have to go all the way to requiring it for authorization, but just requiring it for authentication keeps things out, keeps things from making random requests, keeps you safe from password guessing attacks within your infrastructure.
Right.
And see our examples folder for a previous talk for how to implement this in your application. We have examples of the actual code that is required to use to serve with and use as a HTTP client or gRPC client these certificates.
Right, and it shows how to set up, how a single application can set up different HTTP clients to talk to different sides of the infrastructure. So we've done that. Here's an example, say, of using a Postgres server, one piece of a backend, and an API that's making a call to that Postgres server. So your internal CA will use whatever DevOps automation that you're using to deliver the API certificate to the API application and the Postgres service into Postgres. In Postgres, you can turn on this flag that says mutual TLS. And then when the API is making the call, it can just simply use the certificate that has been given, the single certificate, and hands that to Postgres. And Postgres knows, hey, this is a client from my infrastructure and I trust it. I can continue with the conversation for this. Yeah. So it turns out to be very, very simple to do this, and gives you a tremendous amount of security in your internal infrastructure.
Last but not least, in making this work for your application, monitor your certificates. We're all SREs here. TLS fails very suddenly by design when certificates expire. Monitor your certificates. Prometheus's black box monitoring is drop dead simple to make use of. You can simply set up a black box exporter and then set up Prometheus with a bunch of targets. You just query the black box exporter with a target name, and it will go query it. It will run a TLS connection. It will run an HTTP GET request over HTTPS, and it will print out when the shortest certificate in that chain expires as when the last certificate in that chain expires. This is great. With a proper ACME setup, you should be rotating at least 1/3 of the way through your validity period, and you can set up your alerts so that you are alerted days or weeks before the certificates actually expire. So you've got time.
Yeah, and again, setting that list of URLs or targets in your Prometheus configuration is dead bang simple.
Yeah. Well, so remote trust domains. You should probably not use TLS for.
What are remote trust domains?
Right. You should probably not use your private CA for communicating with other business applications,
other business partners,
right?
Like vendors or supply chain suppliers, et cetera.
They should provide you with a public endpoint. But if you are going to communicate with mutual TLS, set up a trust domain that is your business to business trust domain, and get them to send you their business to business trust domain. And then your applications you can load into the applications that need it the keys signed by their trust domain, and they can load into their applications that need it the keys signed by your trust domain. Right.
So it's just building yet another trust domain that crosses the border to that provider's infrastructure.
Yeah. Thank you. If you've got any questions, we'll probably be on Slack, and you can read all about it, our examples, at this URL, or send us an email.
Yes. Look forward to talking with you. Thank you very much.
Thank you very much.